Welcome to Day 9, Factoring in Complex Fractions and Trigonometry. Today you're going to need the 3 P's: paper, pencil, and plenty of patience. That's important. Let's begin. So this entire lesson is focused on the commonalities of factoring between algebra and trigonometry. The 3 different ways that you can factor are greatest common factor, a difference of perfect squares, and trinomial factoring, or as we will get into, freaky factoring. Some of you may have heard of it as funky factoring. In our examples, we will parallel an expression using variables on the algebra side and an expression where the variable is a function of theta on the trigonometry side. In our first example, we will factor using the GCF. That is to say, we will divide a common factor from both elements in the expression so that we have 2 factors resulting from each statement. In example 1a, I notice that I have a GCF of x. In other words, both elements have an x as a factor. I can pull this x outside of the expression, which I have placed in parentheses, and get an equivalent statement by dividing that x from the original terms. This leaves me with an equivalent fully factored statement of x times x plus 1. In example 1b, my variable is not x, but rather the function of theta. In this case, the cosine of theta. If I rewrite cosine squared theta in its equivalent form, cosine of theta squared, and keep my plus cosine of theta, the visual parallel becomes more clear with our algebraic example. Notice the structure of both expressions is the same, with cosine of theta taking the place of x. Here, cosine of theta squared is in the same place as x squared, and the cosine of theta is just in the same place as x. As a result, we will factor the expression in the same manner. We notice that the GCF of both terms is cosine of theta. As such, we can pull a cosine of theta outside the now bracketed statement and gain an equivalent expression by dividing cosine theta from our original terms. After cancellation, we are left with a fully factored expression, cosine of theta times the cosine of theta plus 1. In our second examples, we will factor by using the difference of perfect squares, or for the shorthand, DOPS. In example 1a, I notice I have 2 different variables, x and y, and both variables are squared. I also notice that the operation between the 2 variables is subtraction. As such, I can use the difference of perfect squares. I start by writing a set of 2 parentheses and placing x on the left side of both sets and y on the right side of both sets in the same manner they are subtracted. Next, I place an addition sign in one factor and a subtraction sign in the second factor, thus completing my difference of perfect squares. In our trigonometric function, we notice we have 2 variables in sine theta and cosine theta. Both are squared. Rewriting our expression allows us to see the parallel with 2a, and the difference of perfect squares becomes more clear. We solve in the same fashion by placing cosine of theta on the left and sine of theta on the right of both sets of parentheses in the same order in which they are subtracted. We then add a plus sign to the left factor and a minus sign to the right factor, completing our difference of perfect squares factoring. In our third example, we will utilize the trinomial factoring method. In example 3a, we notice we have a quadratic expression, which means we will have 2 factors. We draw 2 sets of parentheses and place x in the first term of both, as the first terms must multiply to x squared when we FOIL. Next, we look at our last term, 2, and determine the factors of 2 that will add up to the coefficient of our second term, negative 3. In this case, we get negative 2 and negative 1, which we place in our factors alternatively. Similarly, in example 3b, I notice I have a quadratic with my variable being tangent of theta. I can rewrite the statement to show a visual parallel to our original expression in 3a. Once again, I will solve in a like manner by setting up 2 factor sets and placing tangent of theta as the first term in each set. After that, I will look for the factors of the third term that add to the coefficient of the second term. Since I have 2 and negative 3 again, I once again get negative 2 and negative 1, which I place in the parentheses alternatively. Notice that in all 3 cases we have investigated that the variable is not just a letter but a function of theta. You must learn to see these function statements as abstract variables in order to manipulate the expressions more fully. Example 4 is completed in the same manner. Pause the video and try it out on your own. How did you do? Compare your answer to the one on the screen. Note that because the factors are the same, it is okay to write your answer as 1 factor squared. In example 5, I noticed that simple factoring will not work because our first term has a coefficient of 2. This means I will have to use my freaky factor method to find the factors of the expression. I start by rewriting my equation so that I can easily see that cosine of theta is my variable. I then begin my freaky factoring. I start by drawing 2 sets of parentheses for my factors. I continue by placing my first term, 2 cosine theta, on the left side of the parentheses. Next, I multiply the coefficient of the first term to the last term, in this case 2 to 1, and get a term 2. I ask myself, what are the factors of 2 that will add to the coefficient of my second term, negative 3? This works out to negative 1 and negative 2, which are placed in the factor pairs alternatively. To complete my freaky factor, I must look at my pairs and determine if either of the parentheses has common factors between its terms. In this case, we notice that the second factor has a common factor of 2 in its terms. We divide out the common factor and rewrite our final fully factored form with an expression of 2 cosine of theta minus 1, staying the same, and our second factor being cosine of theta minus 1. And we are complete. In the next examples, we will be asked to simplify complex fractions that use multiple trigonometric functions. Where possible, we will be asked to rewrite these expressions in a form that uses only one trigonometric function, if it's at all possible. To do this, we will follow 2 steps. First, find the common denominator between all the fractions involved. Second, multiply each term by the common denominator and reduce the fraction. You may also find there is substitution and manipulation of the expression to further cancel and reduce that will be required. To do this, recall 3 skills. First, when you have a term to a negative exponent, it means to take the reciprocal of the term to the positive power of the exponent. In other words, b to the negative first equals 1 over b to the first power. b to the second power, or to the negative second power, equals 1 over b to the second power, and so on and so forth. Remember your reciprocal trig functions and how they can be rewritten in terms of sine and cosine of theta. You can also recall that tangent and cotangent of theta can be rewritten in terms of sine and cosine of theta, as is shown here. Finally, we introduce a new substitution which you should memorize quickly. This is sine squared theta plus cosine squared theta equals 1. This will henceforth be known as in your notes as Big Papa because it is so important to remember this expression. Many different formulas can be derived for it, so memorize it. You have been warned. Assuming the statement to be true, we have 2 consequences that result. By subtracting cosine squared from both sides, we find sine squared theta can be rewritten as 1 minus cosine squared theta. Similarly, if we subtract sine squared theta from both sides, we find that cosine squared theta can be rewritten as 1 minus sine squared theta. These 2 consequences of your Big Papa equation will be very helpful in substitution later on in our examples. In example 6, we are told to simplify the complex fraction and rewrite it as a single trig function if possible. To begin, we need to look for the common denominator. To do this, we make sure all of our terms in the top and the bottom are fractions by placing the constants over 1. We see in the bottom that we have 1 minus 1 over cosine of theta, so we're going to place that 1 over 1. Now we have all fractions. We can easily see that the common denominator here in all 3 fractions is cosine of theta. Next, we must multiply all of our terms by the common denominator. That is to say, we multiply the terms in the top and the bottom by the common denominator cosine theta over 1. Here I write cosine theta over 1 in the top and in the bottom. To avoid confusion, make sure that you place parentheses or brackets around the expressions that have multiple terms, such as in the bottom of our complex fraction. This will also help you to remember to distribute properly. Next, we rewrite the results of multiplication in the top. We get cosine theta over cosine theta. And in the bottom, if we have distributed correctly, we should get cosine theta over 1 minus cosine theta over cosine theta. Next, we cancel and reduce, where necessary, as shown, and rewrite our expression. In the top, we should have 1 left over, and in the bottom, we have cosine of theta minus 1. And we are complete. This is the simplest form. In our final examples, we will use the same method, but we will need to either rewrite one or more terms of the expressions in order to fully simplify. Let's start with example 8. As always, I start by finding my common denominator. In this case, sine theta times the cosine of theta. Next, I will multiply my common denominator over 1 to all my terms, placing parentheses around my original expressions in order to assure I distribute properly. Here are my parentheses. And now I am multiplying by my common denominator, sine of theta, cosine of theta, over 1, both in the top and in the bottom. If I distribute properly, I should be able to rewrite my expression with the results of my multiplication. In the top, sine theta cosine theta takes the place of the smaller numerators because they are multiplied to 1. In the bottom, I end up with squared terms in the numerator because I am multiplying to similar bases, i.e. sine theta times sine theta will give you sine theta squared, and the same with cosine theta. My next step is to simplify the terms that can be simply cancelled out using like terms shown here. I then rewrite my expression in the simpler form that results. But hold on, I'm not done yet. It's simpler, but not simplest. In other words, I still need to keep going. Notice the new denominator is the difference of two perfect squares. So I can rewrite my entire expression with the factors in the bottom. This allows me to once again cancel the numerator with a factor in the denominator, resulting in the final answer shown in simplest form. In example 8, we notice that one of the terms in our numerator is raised to a negative power. Well, what should I do? I note that I can rewrite this term, sine to the negative 2 of theta, as the sine of theta raised to the negative power of 2. Now I use the law of exponents to rewrite this as 1 over the sine of theta squared. I bring this down into my fraction, rewriting, and carry the remaining term in the top. In this case, subtracting 1, or 1 over 1. I also rewrite my terms in the bottom to make it more clear what my variables will be. I can now simplify the problems as in my previous examples. I start by finding the common denominator, in this case sine of theta squared, and then multiplying through to each of the terms. I cancel and rewrite where I can, and as necessary, until I reach 1 minus sine of theta squared over cosine of theta squared. Once again, this is simpler, but not simplest. If I notice, the numerator is a consequence of my Big Papa equation, and can be rewritten as the cosine of theta squared. Now, I can cancel the numerator and the denominator terms to reach a final simplest form expression of 1. And I'm complete. Here are the skills you should be able to do. If you are having trouble with any of these, go back and re-watch the video focusing on the skill you are struggling with. Until next time, this is Mr. Mackman signing off.